Hello grade 11s and welcome to question number 2. In this question we're going to be taking a look at intermolecular forces and the way it affects different physical quantities such as boiling point and vapor pressure. As always, try the questions first, and when you're done then watch the video to see if you're on the right track. So question 2.1 says the graph of molecular size versus the boiling point is given below. The letters A, B, and C represent the compounds CH4, C4H6, and C3H8 respectively. Oops, I have noticed a mistake. So this one in the middle should actually be C2. So it's C2H6, not C4H6. Okay, so we have these different compounds and they're represented by A, B, and C respectively. And we can see that we have a graph of molecular size versus boiling point in Kelvin. We see that as the molecular size increases, the boiling point increases because we have a straight increasing line as we go from A to B to C. So question 2.1.1 says, define the term boiling point. It's very important that you define boiling point correctly, please. This is a definition that you have learned since grade 10. We say the boiling point is the temperature at which the vapor pressure of a substance equals the atmospheric pressure. Or you can say it equals the external pressure. That is also okay. Now, I would not award 1 mark for saying the temperature, but 1 mark or 2 marks for the entire statement being correct. So if you said the boiling point is the point at which the vapor pressure of a substance equals atmospheric pressure, you get 0. If you leave out any of the rest of the statement, you're also going to get 0, okay? That is how I would mark it, but of course, if teachers would like to be lenient, they may give 1 mark for the term temperature. But please remember, boiling point is not just a point, it is the temperature, and that gets you 2 marks. 2.1.2 says, describe the trend in the boiling points of the compounds as shown by the graphs. So as mentioned earlier, we can clearly see that as the molecular size increases, the boiling point increases. That is shown by the straight increasing line. So for 2 marks, we can say the boiling point increases from A to C. Okay, they say describe the trend in the boiling points of the compounds, and that is why we say it increases specifically from A to C instead of saying the boiling point increases as the molecular size increases, and that is going to give us 2 marks. Then question 2.1.3 says, explain the answer to question 4.1.2. That is a mistake. This should be 2.1.2 by referring to the molecular size, the type, and strength of the intermolecular forces. So in this question is out of 3 marks. Let's start off with molecular size. We see that the molecular mass increases as we go from A to C. So for writing that down, we get 1 mark. We know that the type of intermolecular forces is going to remain the same. All of these compounds are non-polar molecules. So if I draw it for you, we have CH4. It looks like this. Then we have C2H6. Compound B looks like this. And the very last one, compound C, looks like this. These are all organic compounds. It's called methane, ethane, and propane respectively. That is what these compounds actually are. And as you can see, they are symmetrical molecules and therefore they are non-polar. So when we have non-polar molecules, we refer to London forces, or you may speak of dispersion forces or induced dipole forces. So the type of intermolecular force is London forces. For stating that all of these compounds contain London forces, you're going to get 1 mark. That is basically the control. We've mentioned the independent variable and we've mentioned the controlled variable. Now, as the molecular mass increases, the number of London forces or the strength of the London forces is going to increase. Yes, all of them have London forces between them, but as a result of the increase in surface area, we know that between two C3H8 molecules, we have a lot of area, and therefore there's more room for these molecules to interact. There's a greater surface area. So we can therefore say that as the molecular mass increases, the strength of the London forces is going to increase. Or we can even say as the surface area increases, the strength of the London forces increases. And that is the dependent variable. You're going to get 1 mark for that. Okay, so first mark for saying the molecular mass increases from A to C. 1 mark for saying all of the molecules contain London forces, and your third mark for saying that the strength of the London forces increases as the molecular mass increases. That is your 3 marks for question 2.1.3. I would write out 3 bullet points instead of the 2 that are displayed to your screen. Whenever you're asked to explain something, please use bullet points. It helps you to see what you are writing down for marks. And we generally try to write down an independent, a dependent, and a controlled variable in our answers so that we can be awarded the 3 marks allocated. Now, question 2.1.4 says, which one of the compounds, A, B, or C, has the highest vapor pressure? Explain the answer by referring to the data. So, the substance that has the highest vapor pressure is the one that has the lowest boiling point. And the reason for this is because when a substance has a high vapor pressure, it means that the intermolecular forces are weak, and therefore it requires less energy in order to overcome those intermolecular forces. So by referring to the data in the table, we can answer question 2.1.4 by stating that the correct answer is CH4, and the reason is because CH4, or you can refer to it as A or methane, has the lowest boiling point. We know that when a substance has a high vapor pressure, it has a low boiling point. When it has a low vapor pressure, it has a high boiling point, and so on. So this is your answer. 1 mark for stating the substance and 1 mark for stating it is because this compound has the lowest boiling point of compound A, B, and C. We still have a few more questions to work through. That is question 2.2. And question 2.2 says, consider the 2 molecules in the table. We have ammonia and phosphine. We see that the molecular mass of phosphine is missing. We've been given the formula of each compound, and they have different boiling points given to us in degrees Celsius. Now, very quickly, phosphine has a lower boiling point than ammonia. Lower because if you are looking at the number line, we know we have negative 33, and a number lower than that is negative 87,4. Negative 87,4 is a colder temperature than negative 33. So question 2.2.1 says, determine the molecular mass X of phosphine. So if we're looking for the molecular mass of phosphine, we're going to make use of our periodic table. We see phosphorus has a molecular mass given as 31. So we say M of pH3, the molecular mass, is going to equal to 31, plus hydrogen has a molecular mass or an atomic mass of 1, but there are 3 of them, and this gives us an answer of 34 grams per mole. For writing down 34 grams per mole, you're going to obtain 1 mark. That is your answer to question 2.2.1, 34 grams per mole. 2.2.2 says, explain the difference in the boiling points by referring to the type and strength of the intermolecular forces. Now, you may be tempted to speak of the molecular mass. You may assume that both of these molecules contain London forces, for example, but that is not true. So if we are looking at the different molecules, ammonia and phosphine, They both contain 3 different atoms, and they both take on the structure which we refer to as trigonal pyramidal. And if you look at the screen, you'll see over here we have these structures represented more or less in 3D. In phosphine, we have on the phosphorus a lone pair and on the nitrogen a lone pair. But how about we compare the electronegativities? Hydrogen has an electronegativity of 2,1. Phosphorus also has an electronegativity of 2,1. So everywhere in this molecule we have an even distribution of electrons or an even distribution of charge. Therefore, phosphine is actually non-polar. Even though it has a non-ideal structure, it is a non-polar molecule and a tricky non-polar molecule because all of the electronegativities are 2,1, and we often miss this because we immediately assume that because the atoms are different, the electronegativities are going to be different. But always take a look at your periodic table. If we take a look at ammonia, ammonia has nitrogen, which has an electronegativity of 3,0. Hydrogen is 2,1. And we therefore know that this substance has a slightly negative side and a slightly positive side. So since it has a slightly negative and slightly positive side, we can say that ammonia is polar. Non-polar molecules in the substance, so between a phosphine molecule and another phosphine molecule, we're going to have London forces because it is non-polar. Between polar molecules, we either have dipole-dipole forces or a special type of intermolecular force called hydrogen bonds. So between an NH3 and another NH3, we are going to have what we call hydrogen bonds. In your explanations, please don't use HB. Write out the words hydrogen bonds. And we know that this substance will contain hydrogen bonds because in each molecule is nitrogen bonded directly to hydrogen. Hydrogen bonds occur in substances and between molecules that contain within them hydrogen bonded to nitrogen, oxygen, or fluorine directly. So ammonia contains hydrogen bonds. We know that hydrogen bonds are the strongest type of intermolecular force that we deal with, while London forces are the weakest type of van der Waals intermolecular force. So now that we've analyzed these molecules, we've seen their different shapes, we've seen the one is polar, the other non-polar, and we've identified the type of intermolecular forces. Let's now answer the question. I will give the marks, or I would give the marks differently from what this memo says. I would give 1 mark for stating that between molecules of phosphine we have London forces, while between molecules of ammonia we have hydrogen bonds. I would not state in addition to London forces, although in ammonia we also have dipole forces and London forces, we don't state the weaker intermolecular forces. We only state the strongest type of intermolecular force for 1 mark. Then I would award 1 mark for your stating that hydrogen bonds in ammonia are stronger than London forces in phosphine. That is going to get you your 2nd mark. I'm going to give the last mark for stating, therefore, more energy is needed to overcome the intermolecular forces in ammonia than in phosphine, and that is going to be your 3rd mark. Okay, so that is your 3 marks. We normally, whenever we answer questions about intermolecular forces, we try to state the type of intermolecular forces, which one is stronger, and we state the energy needed to overcome not the bonds but the intermolecular forces. Bonds are intramolecular forces, and the intermolecular forces that we're dealing with here don't exist inside of the molecule but between different molecules. Okay, if you find that the molecules contain the same type of intermolecular force, then you're going to compare surface area, you're going to compare the length of the different molecules, you're going to compare the molecular mass, because when the molecule is bigger, then we have more London forces. But otherwise, always be sure to mention these points. And grade 11s, this brings us to the end of question number 2. In the next video, we're going to begin with question number 3, which deals with quantitative aspects of chemical change, a very, very important section of work in grade 11 because you're only going to build on it in more detail in grade 12. So please be sure to join me there. This is not only an investment in your grade 11 end of year results, but grade 12 as well.